So for orbits in uniform circular motion, we're going to be applying this formula, which we kind of came up with in one of the examples during class. Again, this applies to orbits that are approximately uniform circular motion. So I'll be using this formula to try to calculate the mass of Mars. I'll just rearrange it for m. And we're going to use the data for Phobos, because we've got both the radius and the speed of Phobos. So to rearrange this for m, I'll start by squaring both sides. Next, I'll multiply both sides by r. And finally, divide both sides by g. So that can be used to calculate the mass. I'll sub in the values, but I've got to be careful in terms of my SI units here. The radius of Phobos, both the radii are given in kilometers, but these formulas need to be in meters. And same with the speed. The speed is given in kilometers per second. I'm going to have to be using meters per second in this formula. So for kilometers to meters, I multiply by 1,000. So the radius will be 9377 with 3 more zeros. And then the speed squared over the g value, which is a universal constant. Okay, so I will calculate that out. And I am getting 6.43. I'm going to go to 3 sig figs based on that denominator value there. Times 10 to the 23. This would be in kilograms. So I'm going to just go on Google here and quickly look up the mass of Mars and see how close we got. So Google is giving me a value of 6.39 times 10 to the 23. So that's a little bit different, not too much different than what we calculated here. So perhaps some of the numbers we were given here are rounded a little bit. Part B, what is the speed of Deimos? So the other moon. I can use the same equation, and now that I know the mass, I can just plug it in. So I'm just going to go ahead and fill in the numbers straight away to get the speed of Deimos. So g now the mass that I just calculated, and now the radius of Deimos converted to meters, so 3 more zeros, and that should get me the answer. So we'll go in the calculator and we'll get all of that. I did not delete my previous answer for the mass, so I can just, in my calculator, just continue from there. Say multiply by the g value, divide by the radius, and then square root the whole thing. So I'm coming up with 1,352 meters per second. This would be, again, to 3 sig figs. Okay. C. What are the periods of each orbit? So period means the time for one full revolution. That's what period means. I'll say a full orbit. Less letters to write there. So for this, since it's going at a constant speed, we can actually use the speed equals distance over time formula. Capital T is generally the symbol to use for period. Rearranging this gives me time equals distance over speed. Now in this situation, since it travels in a circle, one full circle, the distance will be equal to the circumference. And the circumference of a circle is 2 pi r. So those are the values I'm going to sub in here. 2 pi, the radius, big number. Oh, I guess I have to choose which planet I'm doing. Let me do Phobos first. Okay, so for Phobos, I'm getting a period of 27,557. So what would the units of this be? So period is a time, so I need some time units here. So I used meters for radius, I used meters per second for speed. So this time is going to end up being in seconds. So let's convert that to something a bit easier to estimate. So I'll divide that by 60 to get it into minutes. I'll divide it by 60 again to get it into hours. And I'm not liking what I'm seeing. This is less than 8 hours. Maybe. Let us go on Google here. Orbital period of deimos. Oh, sorry, Phobos. Orbital period of Phobos. 8 hours. Okay, so that matches what we got here. That's pretty quick. Our moon goes around our Earth in close to a month, so I guess these moons are a lot different than ours in terms of their orbits. I won't do it for deimos. You would do the exact same thing to get the period of deimos. According to Google, it's 30 hours, so you can check your answer there if you do it. All right, part D. Suppose there was a third moon of Mars. There isn't, but suppose there was a third moon of Mars that travels at double the speed of Phobos. What would the radius of its orbit be? And I'm going to do this in a different approach here. Just going to recopy down the formula for orbits. Now, our goal is to have an orbit where the object is going at double the speed of Phobos. So our goal is to double V. And how can we get v to get doubled? Looking at the other side of the equation, we have capital G, which is a universal constant. We can't do anything about that. M stands for the mass of Mars. We can't do anything about that. R stands for the radius of the orbit. And that's the only thing we can kind of manipulate for this third fictitious moon of Mars. We have to decide on the radius. That's going to end up giving this a speed that's double the speed of Phobos. So basically, I need the left side of the equation to be doubled. So that means I need the right side of the equation to be doubled. And that is going to be accomplished by replacing the radius with 1/4 of the radius. And the reason for that is because, first of all, radius is in the denominator. So I actually need a smaller radius to get a higher answer. So 1/4 is a smaller radius. But why does it have to be 1/4 of the radius and not a half of the radius? That's because there's a square root there as well. So when I combine that effect, this whole thing's going to end up doubling the fraction. So my answer is going to be it's going to be 1/4 of the radius of Phobos. One quarter of the radius of Phobos. So that's 1/4 of 9377 kilometers. And that is going to be 2,344 kilometers. Okay, so I did that by analyzing the equation. You can check my answer if you wish. You can plug in that value for the radius into that formula and come up with the speed. And hopefully the speed is equal to double of the speed of Phobos. You could have solved this problem purely algebraically. Like, you could have just doubled the speed of Phobos and plugged that in for v, and then isolated this equation for r and calculated it out. And you should turn up with the same answer. I want to, as I said in class, try to start getting you a bit more used to not plugging in all the numbers and just really focusing on how changing one variable affects some other variable in an equation.